Welcome to the Picture Language Seminar. It's a real pleasure today to have Arthur Parzygnat from MIT. He's going to tell us about time reversal symmetry for quantum measurements.
Okay, thank you so much for the invitation, Arthur. So for those of us who are here or online, feel free to just pause and ask me any questions at any point. This is really just to give you an introduction to some ideas I've been thinking about lately. So with that, I'll begin. So this is a talk about time reversal symmetry for quantum measurements, and the idea stems from the following operational scenario. So imagine Alice is making a measurement of some quantum system. And that quantum system, if it helps, you can think of a qubit, and I'll talk about the specifics in a moment. But the idea is that Alice makes a measurement. Alice measures, and Alice gets some outcome. And when a measurement takes place in quantum mechanics, that alters the state of the system. After the measurement, you can imagine that the state is then evolved under some dynamics. It could be unitary dynamics or it could be a stochastic dynamics. And then let's say somebody else, Bob, on the receiving end, receives that state, which is now altered a little bit from what it was before, based on not only the measurement, but also the evolution. And then Bob makes a measurement of that state and then gets also some outcome. And when you look at the statistics of what measurement outcomes you get, you can find the expectation value. So this leads to expectation values for the both measurements. So let's say Alice measures observable A and Bob measures observable B. And we can sort of imagine that there is, in some sense, time is moving forward. Alice makes the first measurement, the system evolves, Bob measures the second measurement B, and we associate time with this. You can also ask if, for instance, if Bob makes a measurement first, uses this state that Bob has access to, and then tries to push that state back towards Alice by some new evolution. So you could imagine Bob now has this state that Bob receives after the evolution statistically. So Bob has that state. And then Bob measures B. But now Bob is making the first measurement. And you can ask, is there an evolution that goes in some sense back from Bob to Alice, such that when Alice makes a measurement of that quantum state after the measurement of B, so Alice will also measure exactly the same observable A. And the question is there an evolution So is there an evolution going backwards that nevertheless gives the same expectation values? So this is the general question that I will be answering today. And um, and first, let me say why this is not something that should be surprising if you think of just purely classical stochastic systems and processes. So classically, what represents Alice making a measurement and then evolution and Bob making a measurement? What we have is input state, the input state is some probability distribution. Let's call that the probability of measuring input, let's call it X, for example. So classically, we have some probability on some finite set X. These are the possibilities that Alice has access to. And so you can make a measurement, maybe one of the outcomes of X, and that has some probability P of X. Well, what represents dynamics? In this case, evolution, after I make an observation, is given by a set of conditional probabilities, P of Y given X, which basically just tells me if I measure X, what is the probability of measuring Y when that state is received by Bob? So you have an evolution that's described by a transition probabilities, conditional probabilities. And let's say we have an observable. Let's call F an observable for Bob. This just means it's some function on X. So F of X is, for each value of X, we get some number, like the price of some stocks, for example. And let's say we have G is an observable on Y. So we have G of Y. Then what I can look at is I can compute the joint expectation of measuring observable F and then observable G. And the result of that is the joint probability of measuring both of those. So the outcome here, so this, let's call it a 2-time expectation value. The outcome of measuring, for example, F followed by G, so I read this as F followed by G, is equal to a particular sum where I take measuring F of X, measuring G of X, and then multiplying by the probability of X occurring and Y occurring. So it's the joint probability. The joint probability is just the product of these two probabilities and conditional probabilities. So what we do is we sum P of Y given X times the probability of X. So this is the probability of both X and Y occurring, given the fact that the evolution from Alice to Bob is given by some conditional probabilities, multiplied by, oh, this is G of Y, multiplied by the values of those observables for those specific inputs and outputs. And what do we mean by a reverse evolution in this case? So this evolution would be another set of conditional probabilities, but this time in reverse. So probability of X given Y. And there's a very well-known formula that relates these different conditional probabilities. Does anybody know what it is? Bayes' rule. Exactly. So Bayes' rule tells me that what I can do is I can replace this 2-time expectation value of measuring F followed by G. And I can rewrite it as F comma G is equal to sum XY, probability of X given Y, times the probability of Y, and then plug in exactly those same functions, but I'll just write them in reverse. P of Y times F of X. And so if I rewrite this, so this is by Bayes' rule, this step in the equality here, where the probability of Y is really, I should think of that as what is the state that Bob has access to statistically. If I rerun this experiment over and over and over again, the state that Bob has access to is the probability of Y, which we can write using the conditional probability and the ordinary probability P of X by summing over all possibilities in X. And if I rewrite this using this same notation that I introduced of a 2-time expectation value, I can interpret this as saying Bob makes the first measurement and then Alice. So in the case of classical ordinary probability theory, the answer to this question is, dare I say, almost obvious. There's always a collection of conditional probabilities that allows me to deduce such a symmetry in terms of measurements forward and backwards in time. Or inferential measurements if you're not actually reversing the order of time. So that's the setup that we have so far. But what we want to do is we want to analyze what happens in the setting of quantum mechanics, where we have to be careful because in general, measurement alters the state of a system, and we have to check or verify whether or not such an evolution exists. And formalize what that actually means. In fact, how do we actually define all of these quantities from the classical setting to the quantum setting? So the first part of this talk will be a little bit of a review of some of these ideas from quantum theory, and then we'll extend these ideas to the quantum setting as well. This is a good time to ask questions. Everything good so far? Okay. Good. So now let's recap some static quantum. So in static quantum, what we deal with, what represents a state is represented by a density matrix. So this is a density matrix is a matrix rho. Let's fix some dimension of our quantum system. So if we're dealing with qubits, it'll be 2 by 2 matrices. So we have a matrix rho, which is positive, and its trace is equal to 1. So this is what a state is represented by. And if A is an observable in the quantum mechanical sense, so it's a self-adjoint operator, this means A dagger equals A, then there are two things we can do with this. First, every self-adjoint operator can be diagonalized. And so there's a spectral decomposition. So let's say if A is an observable, and we write A as the sum of the eigenvalues weighted with the corresponding projections. So in this notation, lambda is an eigenvalue, and pi is a projector onto the eigen subspace. So if there's a degeneracy, this projector is landing onto the full subspace. It's not necessarily rank one. This is important. So if A is an observable and I have a spectral decomposition, then I can use a density matrix together with a state to define the expectation value of A in that state. So given this information, the expectation value of A in the state rho is, does anybody know what, I think everybody does, so maybe we should get some participation. What's the expectation value of an operator in any state rho? What's the formula we would use? Trace rho A. So the expectation is trace rho A. Let's also rewrite it using this spectral decomposition too, to make a little bit more of an analogy to the classical case. So we can write it like this, or we can calculate, lambda is just a number, so it goes through the trace, and we get trace EI times rho. Now, this is very, very similar to the expectation value of a classical function, where this is the probability. I think of this as the probability of measuring outcome I, and this is the value of my function. This is the value of my classical observable, where the finite set is indexed by I. So this is one way of thinking about what the expectation value is of a state in rho, of an observable A in the state rho. This is the definition of expectation value. So an example, it's always good to draw some examples. So let's look at a qubit. So in the case of a qubit, every density matrix rho can be expressed as 1 plus z x minus iy, x plus iy, 1 minus z, where x, y, and z, this is a vector in the unit ball in R3. So this is one way to parameterize every density matrix. So it looks something like this. And so every density matrix is uniquely determined by a single point inside this unit ball of radius 1. And what's an example of a common observable? So an example of an observable A, what observables are you familiar with for qubit systems? Say, yeah, Pauli matrices, right? So we can use Pauli matrices. So let's use Pauli matrix, for example, sigma z. So sigma z is the matrix 1, 0, 0, -1. And let's just say for simplicity, if I have an arbitrary state rho, I can write all these formulas and it'll be a long, complicated process. But let's just take, for example, rho is equal to 1/2 1 plus z, or maybe even take, let's just do this one. Let's just say it's 1/3 and 2/3. So if I have my density matrix like this, where is it on this block sphere, on this block ball? It's somewhere. I interpret this as saying it's 1/3 likely to be in the state given by the vector 1, 0, and 2/3 likely to be in the state given by 0, 1. In this picture, the vector corresponding to 1, 0 is up here, and the vector corresponding to 0, 1 is at the bottom. And what this tells me is that if I look at this operator and I calculate what the expected value is, and if I look at where the state rho is, this state rho is 1/3 likely to be up and 2/3 likely to be down here. So it's somewhere in the bottom hemisphere, bottom part of this sphere, along the line passing through the z-axis. And if I calculate the expectation value of this observable, I'm pretty sure you'll be able to do it while I'm moving these boards. This one. And while I'm doing it, I'll expect an answer. So what's the expected value of sigma z in this particular state rho? Does anybody know? Yeah.
1/3.
It's close, very close. It's on the bottom part of the sphere. So the more weight is given to the negative value. So I think you did the right math, but you needed a minus sign. So the trace of rho sigma z is equal to -1/3 in this case. That's just what happens when I take the product of these two and I evaluate it like that. You can also, and notice, by the way, I'm using this formula. I could write it like this, and in this particular case, it's not so bad to split up this into projectors and then add up all of these numbers and then get the result. But it's way, way faster, in my opinion, to do it like this. If you know what the operator rho is, you know what A is, you just multiply the matrices and compute it right away. If I happen to give you a more complicated rho and some Pauli matrix in some arbitrary direction, it would take you a minute to calculate what it is using this formula rather than the one on the left. Good. So this is how we compute. So this is how we compute. How we compute expectation values for static systems. But the whole point of this talk is to talk about dynamics. So what about dynamical expectation values? Meaning when we include an evolution that the state rho is exposed to. So in this situation, we can make a definition. And what do we need? What's the input that we need to make this definition? First of all, we need a density matrix rho. So given a density matrix rho, and we also need a channel, an evolution. So given a density matrix rho and an evolution, and let's give these things letters. Let's say rho lives in the system for Alice. And then let's say that we have also an evolution. So let's say a quantum channel. And let's say this channel is going from Alice to Bob. And let's call it E for evolution. So this I do need to ask about. Who is not fully comfortable with the idea of a quantum channel? Everybody's totally confident? Are you confident? If I ask you what is the definition of a quantum channel, would you be able to tell me? Thank you. So here's one way to think about it. I won't write the definition because it is a little technical, but one way to think about it is a quantum channel on a system is the analog of a stochastic process for quantum systems. And one way to think about it is if Alice has access to Alice's system, and I want to know what this evolution does, I can imagine Alice embedding her system into a larger Hilbert space and then having a unitary evolution act on both the systems. Unitary is okay, right? Yeah, unitary evolution is acting on the full system, and then you trace out the environment and get some output. All of these kinds of maps that I'm thinking about in this talk are of that form, but I don't want to write all that down. So just think of some stochastic evolution, a noisy channel. So given such a density matrix and a quantum channel, and we also have to do measurements. So now not only is Alice doing a measurement, but Bob is doing a measurement. So, and given observables A, and let's write their spectral decompositions, lambda I, pi. So that's the spectral decomposition of A. And an observable for Bob, let's use different letters though, mu j and qj. So these are projectors, just as before for the spectral decomposition. So given this information, the two-time expectation value of first measuring A, then letting the system evolve under rho, just like in the picture, which is still here, right? Yeah. So first measuring A, then letting the system evolve under the channel E, and then measuring B, we can write down the joint expectation value of that completely analogously to the way that we had in the case of classical systems. Let me just be a little bit more careful about saying that this depends on rho and E. This is equal to, and I can write a formula down, lambda I, mu j, and then this has to be some probability. It's some joint probability of first measuring I, letting the system evolve under E, and then measuring J. And what that probability is, it's the trace of applying your map, your channel E, to the projector, to your density matrix sandwiched between the projectors times the last projector and taking its expectation value in some sense. So this is just a formula. It's a formula for the two-time expectation value. And the meaning is that it's giving me the expected value first measuring A, followed by the evolution E, and then measuring B. So even if you formula seems a little bit, it's messy for a reason. It's a little bit complicated. And one of the things that happens in this formula is that your density matrix rho is sandwiched between two projectors. This has to do with the fact that once you make the first measurement, it collapses the wave function. Yeah.
Sorry, why is P a projective here? I thought you were thinking about like general POVM. That's my
No, I'm not. I'm not.
But you said like quantum channel.
Yeah, the channel between. So what's happening is that the system is evolving. So after you make a projective measurement,
Sure.
the system then evolves, and then I'm making another projective measurement.
I see.
So the system, the evolution is arbitrary, but the measurements I'm doing are just projective in this whole talk.
Okay, sure.
Yeah.
Thank you.
Good. So this is what the two-time expectation value is. And yes, I think I was using this word. But to be honest with you, if I were to try to calculate this, it's a little bit of a mess. I have to find the spectral decomposition of A and B. And so just like in this case, although this wasn't too bad, it was much easier to calculate this. But we're given this. This is the thing that sounds a little bit more intuitive based on our ideas of classical probability theory. So how do we compute? How to compute this more efficiently? Well, let me state a theorem about how to compute these. But first, let me restrict attention to particular types of observables. And the particular type of observables, for instance, in the case of qubit systems, will be Pauli operators. So when I'm talking about qubits or multi-qubits, I'm thinking of Pauli strings or Pauli operators. Those are the types of measurements I'm going to be doing. And I'm going to make a definition for the types of measurements, observables that we'll be looking at, which contain Pauli observables. So we'll make that definition first. And then once we have this definition, then I'll show you a much faster way to compute these quantities and a very interesting theorem about how to represent what replaces the idea of a density matrix in a formula like this. So we say an observable A is called light touch. Is called light touch if A squared is proportional to the identity matrix. It's light touch. And if I think about what A is, A on its own has either one eigenvalue or two eigenvalues. And those two eigenvalues are opposites of each other. They're opposite in sign. So one is positive, one is the negative of it. So it's just two outcomes in some sense, just like Pauli operators have +1 or -1 eigenvalues. So that's what this idea is generalizing. Light touch are things that have two eigenvalues at most, or they're proportional to the identity operator. So that's what it means to be light touch. And as I said, examples, Paulis. For all qubit systems. Good. So now that we have, now that we know what kinds of observables we're looking at, let me state a theorem for such light touch observables. So the theorem says that given the same setup as above, so given a density matrix rho on A and a quantum channel E from A to B, there exists a unique matrix X, which is now in the tensor product of both Alice's and Bob's system. So this just means that it's a matrix, like if I had qubits and this was a qubit system and this is another qubit system, so Alice and Bob are just sharing, they're exchanging a qubit from one to each other, then this would be a 4x4 matrix. So given a density matrix rho and E, then there exists a unique matrix X in the tensor product of those two systems, such that the 2-time expectation value of A followed by B in this state is equal to the trace of X and then A tensor B. And then I need a quantifier because we need to make sense of what this quantifier is saying. And this is true for all, let me write it here actually. It's better here. So this statement is true for all light touch observables, A and B. So it's not true for all observables, A and B, but it's only true for light touch observables. There exists a unique matrix that satisfies this condition. I'm going to pause there because I think that this is a natural point for either people to argue or say something. Yes.
Is there some intuition on like why exactly this like definition of light touch?
Yeah.
Maybe, and like does the light touch somehow like does it include the classical case?
Yeah, so light touch, so I've only defined light touch observables for like matrix algebras here. But the idea behind them is like they're very similar to projections. Projections have eigenvalues 1 and 0. These have eigenvalues like 3 and -3, or 1 and -1. Or they're just the identity operator. And part of the thing about them is, maybe I'll just make this as a remark, but every matrix algebra has a basis of light touch observables. So just like Pauli operators and the identity matrix form a basis for 2 by 2 matrices, every matrix algebra has a basis of light touch observables. And what this means in some sense is that light touch observables form a tomographically complete set. So you can always reconstruct, for example, a density matrix, or in this case, this matrix X that encodes not just the density matrix rho, but also its evolution. Good. So, so this is one fact about this theorem. But yeah, yeah,
X.
yeah.
X is in 1830, right? What do you mean by that?
Oh, good. I used script letters. So this is like the algebra of all of all 2 by 2 matrices, for example, and this is the algebra of all 2 by 2 matrices. So this is one of those 2 by 2 matrices. And another one here. Yeah, good question.
Matrix X times matrix
Right.
A, and then insert like, okay.
Yeah. Good, thank you. Exactly.
What if you have n qubits?
I mean, you could do this too. Yeah, you could just use polystrings. Polystrings form a basis of tomographically complete basis for any number of qubits. Good. So that's one theorem. Okay, well, that doesn't really tell me that much because this is just an existence theorem and a uniqueness theorem. And there's another bonus to it. So moreover, we can actually explicitly calculate what X is. And I'm going to write a formula for X. And it's going to look a little strange. So it's a half times the anti-commutator of two things. So this anti-commutator means, AB is AB plus BA, where A and B are viewed as operators. So it's the anti-commutator of two things. The first one is rho tensor the identity on B, on the algebra for B. And then here, I have to ask this question, but who has heard of the Choi matrix? I want to see hands, as many hands, just heard of the Choi matrix. You haven't heard of the Choi matrix? Okay.
We had a talk by Choi.
That's right, you had a talk by Choi. Good. So actually a majority of this audience has heard of what the Choi matrix is. Good, forget it. And for those who haven't heard it, it's actually very good that they haven't heard it, because what I'm about to write is its cousin, which is called the Yamyalkovsky matrix of the channel E. So the Yamyalkovsky matrix is very closely related to the Choi matrix, but it's not quite the same. So I can write this in many different ways, and depending on whether you come from a math or physics background, we can write it in different ways. Let me write it using Dirac notation. So for example, I can write my matrix elements. This is the IJ matrix, so it has 1 in the ijth entry and 0 everywhere else. Tensor product of E, it looks almost, look, I'm about to write something that looks like the Choi matrix, but I'm going to take the transpose here. So I'm just going to flip the order. So this is actually a 1 in the JI entry, not in the IJ entry as well. So that's what this is. This is the Yamyalkovsky matrix associated with the channel E. And this is very convenient because this actually answers one of our questions, which is how can we calculate these 2-time expectation values in a relatively simple manner? No need to do spectral decomposition. You plug in this matrix X, and you can calculate all 2-time expectation values of light touch observables. So that's what that theorem says. Oh my goodness. Oh no, I started at half an hour. I still have 25 minutes. Okay, good. Okay, great. Why on earth is this helpful with what I was saying about this idea of uh, dynamics moving forward and backwards in time? So let me next address that part. And by the way, while are there any questions so far? I wonder if maybe it's best to do an example first of, of this. So let me go back to the qubit system. Maybe that's what I'll do first. So going back to qubits, let's take a very special case. So let's take rho equals the same one that I had before, but slightly more general. 1 plus z, 1 minus z. So this is somewhere along the vertical axis through the center of along the z-axis. So this is my state is somewhere along this z-axis here. And let's take E to be what's called the amplitude damping channel. What is the amplitude damping channel? I can write a formula for it. So E acting on any state rho is equal to, I'm going to write the formula, but I won't really, we won't really be dealing with it much. But it's good to know what it is, and you can verify what I'm about to say regarding it. So it's this plus an extra term. So this is what it does to an arbitrary density matrix where gamma is some number between 0 and 1. So, you know, there's a formula for what this is here, but I think it's best to see what it does to my set of states after applying this channel E. So here's what my set of density matrix looks like before I've done anything. It's the unit ball. But then after I apply this channel, what happens? So it depends on gamma. So depending on what gamma is, it will push all of these states farther and farther north inside this block ball in this direction. So in this picture, I guess gamma looks like it's roughly a half. And the larger gamma is, the smaller the sphere becomes. And eventually, so this is gamma is large. And here gamma is like, I don't know, a half or something like that. And if gamma is almost 0, then that means there's essentially no damping. And my states, I'm still getting almost all of my states back. So this is gamma, it's pretty small. And so effectively, when gamma is equal to 0, I have the identity channel. And when gamma is equal to 1, large means less than 1. Large but less than 1. And when gamma actually equals 1, all of the states inside this block ball go to the North Pole. So the terminology comes from the fact that I'm imagining this is like the ground state of some Hamiltonian, and my states are flowing towards the ground state of that Hamiltonian under this noisy evolution. Good. So this is my channel E and the state rho that I'm looking at. And what I can do is I can calculate using this formalism. I can write down a whole table of all of the expectation values of measuring Pauli operators. So let's do that. Yes.
Not fall
Yeah.
continuously. So will it eventually vanish?
It will eventually vanish. When gamma actually does equal 1, the after applying E of rho, every state will go to the North Pole. Yeah, exactly. Good. So now let's take so now let's write a table. So this is going to be a table. So Alice measures some observable up on this row. So there are 4 observables that Alice will measure because it's 2 by 2 matrices. So you have sigma 0, sigma 1, sigma 2, and sigma 3. I think I was calling these sigmas z's and stuff like that before. So this is the identity matrix. This is sigma x, this is sigma y, and this is sigma z. So Alice is going to make some measurement. And what we're going to do is then Alice will find an outcome, and then we'll evolve the system under the amplitude damping channel, and then see what happens. And then Bob will make another measurement of sigma 0, sigma 1, sigma 2, and sigma 3. So you can use, you can calculate these either using this formula or using, where did it go? Maybe I've erased it already. Using the formula for spectrally decomposing all of these operators and computing them that way. But this way is particularly nice. And the table that you get, you can write down all these 2-time expectation values, and you get something that looks like this. Part of the reason why I'm showing this to you is also that these calculations are actually not difficult. It's just linear algebra. Okay, so this is what you get for the 2-time expectation values when you actually look at what Alice and Bob measures. Good. So now that we have this, now that we know that we can calculate this, let's try to introduce the idea of what it would mean to find a channel that gives you the time reversed expectation values as a result. So let's make that definition. I will want, oh, I can't bring that up. So let's see. So given our setup, so given a density matrix rho and E, an operational inverse. So I think at this point, this is some of the new ideas. So given rho and E, an operational inverse is a channel. This is going to be a quantum channel that now goes from Bob to Alice. So it is a channel F from Bob to Alice, such that the 2-time expectation value of first measuring A and then B, just like in the, actually it was earlier here, just like in the ordinary Bayes rule, is equal to BA. And what states do we put here? Well, we have to have a state for Bob. What is that state for Bob? Well, Alice has a state rho, sends Bob the state E of rho. It's just the statistical density matrix that describes what happens to rho after the evolution. So that's E of rho. That's Bob's state. This is the analog of that probability distribution on Y. So before we had a probability distribution on X, we had conditional probabilities of Y given X. Then what is the probability on Y? That's the analog of this. And then we use the channel F. So an operational inverse is a channel that gives you the opposite of the order of making those measurements and getting those expectation values. And this is, if it satisfies this for all light touch observables. Right now, this is a definition. It's a definition. I didn't say anything about its existence. But I can say something. So, any questions so far? So in practice, what might happen is that I might not be able to find such an F. So it's not that they won't be equal, it's that the right-hand side, well, I could choose an arbitrary F and try to see if I can make it equal the left-hand side, but then it might not be equal. But I have a theorem for when it exists. So that's what I'm about to write. So the theorem says, and this is in some sense quantum Bayes rule. The theorem says that it's going to say a couple of things. It says if an operational inverse exists under these assumptions. So under these assumptions, if an operational inverse exists, it satisfies the following equation. And this equation is like the analog of Bayes' rule. So that equation reads 1/2 identity tensor rho. The Yamyokowski, I'm going to have to erase some things and specify what all of these things mean. So it's the Yamyokowski matrix associated with not the quantum evolution E, but it's Hilbert-Schmidt adjoint. I'll say what that is in a moment. And this is equal to, well, I guess I can get rid of the halves. Is equal to E of rho tensor 1, comma, the Yamyokowski matrix of F. So if an operational inverse exists, it satisfies this equation. And this equation, so let's take a moment to look at what's going on in this equation, just to make sure, like, how do we solve such an equation? So we know what the density matrix is. So we know this. We know what this is. This is so E star is the Hilbert-Schmidt adjoint of E. So the domain of E has an inner product. The codomain of E has an inner product. So now that we have a map between inner product spaces, are inner products comfortable with you? Good. So we have inner products on the inner and the outer, and we can take the adjoint of our operator of our linear transformation. So that's what I mean by this. So this is known. So we also know this because that's easy to compute, especially if E is a channel. If E is a channel and I wanted to compute the adjoint, what I would do is I would take the adjoint here, and I would just put adjoints. I would put adjoints everywhere. Or no, rather, sorry. I would put this operator on the left and this on the right. They're the same here. And then I would put this operator on the left here and that one on the right there. I would just switch their order. So this is known, this is known. This is also known. Right? It's just E of rho, I plug it in. And the thing that's not known is this. This is what we want. And remember, why is this what we want? Because the Yamyokowski matrix of a map F is equal to, right, we have these, we have ij, and then we have tensor F of ji. So basically what this is that this is a big matrix of the value of F on all of these, on this basis of matrices. So if we know what this is for every single I and j, which this matrix gives us, then we know what the map F is. It's completely determined by how it acts on a basis. So we know what F is, and we can solve it from this equation. This equation is also known as, this equation is known under many names. It's called the Sylvester equation. You probably didn't see this in linear algebra, but this is an equation of the form A equals, not, it's not of the form AX equals B. It's of the form A anti-commutator X equals B. And you have to solve for X. But the point is, it's well understood how to solve this equation. And finding what F is can be obtained from exactly that equation. I don't want to erase this great picture. Maybe I'll erase that. Now, this tells me that if an operational inverse exists, it satisfies this condition. But it doesn't tell me when an operational inverse exists. Right? It only tells me if it exists, this is how I would solve for it. And because of the uniqueness theorem, this is the only solution.
Sorry, do you have any example where you can find an F which satisfies this equation?
Yeah.
But that F is not a operational inverse.
No, they're equivalent.
I mean, like this theorem is a one-way theorem. But
Right, it is a one-way theorem. The other way is also true. If I have a channel F that satisfies this equation, it will be an operational inverse as well.
I see.
This is an if and this. I didn't say the if and only if, but it is an if and only if.
I see.
So in some sense, like I didn't. This isn't a talk about quantum Bayes' rule, but it essentially says if a Bayesian inverse exists, it's an operational inverse, and conversely, if an operational inverse exists, it is a Bayesian inverse. But I didn't define what a Bayesian inverse is. So, but one case of it is something that satisfies that equation. Good. So this is when they exist. Sorry, if they exist, that's what they satisfy. So when do they exist? Unfortunately, as far as I'm aware, the general answer to this question is an open problem still. So in general, not known. In full generality, like a nice theorem. So in full generality, I don't know. But we know in several examples. And in fact, there are some operator algebraists here, so I'll make a comment. A different version of Bayes' rule is related to something called the Tomita-Takesaki modular theory. And in that case, not with the anti-commutator, but with an ordinary product, it is well understood when such a Bayesian inverse exists. And it has to do with the modular conjugation on the domain and the modular conjugation with respect to the Hamiltonian obtained from the density matrix rho on the domain and the codomain. So if there's a certain symmetry that's involved, that's an if and only if statement about the existence of a Bayesian inverse. And this goes back to the to Takesaki's work.
There is an infinite dimensional version of this theory.
There should be an infinite dimensional version of this theory, yeah. But I'm only looking at it for quantum information purposes, yeah.
Oh, sorry. I was going to ask the same question. Like you're talking about the type 1 from algebra, but
yeah,
there should also be.
I expect that there should also be. The only thing that you would probably have to do is not use the Schrodinger picture, but use the Heisenberg picture. You should be able to generalize these things, though I don't think that's written in full generality.
But I think, sorry, I'm a little bit confused because do people know how to actually formulate measurements, like let's say tabulate out in algebra?
Yeah, so what I'm saying specifically is referring to this type of equation.
Oh, I see.
I don't know how to address the operational perspective.
I see.
Yeah. Good question. So, right, when do they exist in full generality? I don't know, but we know in several examples. So let's look at this example. So where we have an amplitude damping channel. So E is amplitude damping. In the case where it's amplitude damping, then the theorem says, I don't know if I want to call it a theorem, but maybe I'll just call it a proposition. It says that given rho of this form, 1 plus z, 0, 0, 1 minus z, and the amplitude damping channel for arbitrary gamma, an operational inverse exists. Exists if and only if. Sorry, I don't remember the inequality. Yes. Z is greater than or equal to gamma over gamma minus 2. So that's when it exists for this example. Right. So, okay, good. So what does it look like? Oh, good, I didn't erase this. And I can write down an explicit formula for it. So if it exists, I can write down a formula for it. And maybe I'll say a little bit about what it looks like in a moment. So this is what happens when you apply E to the block ball. When you apply such an F to the block ball, now think of, I'm trying to like kind of invert something. So if I'm shrinking the block ball, inverting it is going to expand the block ball, not a positive up, like that's not a quantum channel because it takes states to things that are not states. So taking the inverse is not going to work. Okay, so what's the next thing we can do? Well, if we're pushing the block ball up and shrinking it, maybe your natural guess would be we're going to push the block ball down. And well, we can't expand it, again, because expanding would lead us outside of density matrices. So it doesn't quite do that, but it does something very similar. And I guess in the case when gamma is somewhere like this picture here, it doesn't quite squash it down like this. It's not like an amplitude damping where you've switched your ground state. Instead, it's that combined with what's called a dephasing channel. So it ends up looking something like you squash it down a little bit, but you've also shrunk it along the equator. So this is what happens when I think gamma is roughly, I think if this picture is correct, roughly when gamma is 0.6, this is what happens to the block ball after you apply the channel F to it, when it satisfies this condition, when Z satisfies this condition. Okay. Now, the theorem tells me that if I calculate these expectation values, then I should, the only thing that changes is that now Bob is measuring first and Alice is measuring second, and they acquire the same expectation values. And if you use this channel F here to calculate those expectation values in exactly the same way, you will find the same table. And so maybe since it is 5:30, I wonder if I should conclude and maybe say just a little bit of a summary, which is that this is just a particular example of looking at what happens and how you can find such an operational inverse. And we have a characterization theorem for that. some modifications will allow you to get a little bit more than just this. But in general, it's largely an open question as to what are the necessary and sufficient nice looking conditions that guarantee that the existence of such an operational inverse F. And although we can always solve for this as a linear operator, as a linear map, the key problem with this is that that linear map is not always taking you from states to states. It might take you from states to outside of states. And what we really need is that this to be a completely positive map. And that's where these restrictions come in. So thank you.
Thank you very much for a nice talk. And are there questions here? Yes.
Yeah. One thing I find very interesting is that I think that theorem implies like generically, you don't really have a operational inverse.
Yeah, because you need it to be positive.
Yeah, like
right.
I mean, what's the implication of that? Like, does that mean quantum measurement formulated in this way is not time reversal symmetry?
It's not. Yeah, I would say if you think in terms of light touch observables alone. I mean, these are the ones for which we actually had a theorem in the first place, so we were pretty happy about that. Right. But this is sort of telling you that, or at least it suggests perhaps that there may be a form of time, like an intrinsic time asymmetry in quantum theory that is quite distinct from classical theory, because classical theory at the level of Bayes' rule has such a symmetry.
I see.
Yeah. And in some sense, we're trying to get to the bottom of that asymmetry. This is like a step in that direction, you could say.
I see. I think it's also probably natural to think that, say you have rho and like quantum channel E.
Yeah.
When formulating this theorem, if you like use Hall measure to randomly pick up rho, and then randomly pick up E, presumably that will not admit.
Right. You mean if I randomly select these states and density matrices, I would suspect that it would not in general.
But probably it has approximate operational inverse.
It might.
Yeah. That's
Yeah, that's an interesting question. Maybe there's like some interesting way to perturb this. And there are also ways to like perturb the analogous result from Tomita Takesaki modular theory, which was used in like surprisingly entanglement wedge reconstruction.
Yeah.
Is there a qubit version of this?
Yes. Wait, this example or this theorem?
The theorem.
Yeah, this theorem holds in total generality, at least for finite dimensional systems. We didn't explicitly do infinite dimensional, but I suspect that we should be able to. I guess maybe not this part, but at the very for arbitrary qubits systems, this theorem holds. Using light touch observables, like what is the generalized? Like how should we generalize Pauli observables to arbitrary qubits? The idea is to use light touch observables.
And could you outline the connection to the Tomita Takesaki theory?
That might take me some time. The equation in that case would be identity tensor rho times this operator. And that's supposed to equal E rho. Sorry, yeah, I did that right. Tensor 1 times J of F. F. And I'll just say briefly what happens. You can solve for F from this equation because it's just a linear, now it's literally linear algebra without anti-commutators. I can solve for F. F is going to be some map from B to A. And then in order for F to be completely positive, one can show it's equivalent for F to be self-adjoint, meaning that it sends Hermitian matrices to Hermitian matrices. So that's less than being completely positive. But it turns out that being self-adjoint is equivalent to being completely positive. And in this case, being completely positive is equivalent to a certain modular equation to hold. Let me maybe write what that equation looks like so that you can maybe see. So, E, right, E goes from K to B, and let me see. Right. So the condition, yeah, this is the condition that has to hold. So here it's add to the row on T. So you can show that being this map being self-adjoint is equivalent to being completely positive is equivalent to the condition that I'm about to write. So I here is the imaginary number. And add of any operator V acting on some matrix A is equal to V A V dagger. So if this equation is satisfied, you can show that. So you can show that this equation is equivalent to this one after working through it quite a bit. And it's not trivial, but you can show that this condition for all t is equivalent to this one. And this
so rho becomes the modular operator?
Yeah, rho is the modular operator on the domain, and E of rho is the modular operator on the codomain. Mm-hmm. However, in general, this is much more the existence of such an F is in general much more restrictive than the existence of the Fs that I've been speaking about today. Yeah. So it's very, very rare to find solutions to this. This is less rare, at least in my experience.
Are there any questions online? I guess not. So if there are no more questions here, let's thank Arthur again for a very interesting talk.
Thank you.